thank you very much for introduction, and thank you very much for inviting me to this wonderful place. So I'm Yuki SHIOMI from University of Tokyo, and today I'd like to talk about our recent work on spin-caloritronics. So, okay. This picture is our group photo, so taken 2 years ago. So now we have 1 staff and 5 students. And our staff, Dr. Yokoguchi, is a famous young researcher in SCARMIO physics, and he will come to Mainz in September for different SPICE workshop. And Nakagawa is our student, is a main player of this talk. Okay, so my talk is about spin-caloritronics, and spin-caloritronics focuses on the interaction with heat and spins, and various new phenomena have been found in this field. For example, spin-dependent Seebeck effect was found in 2010, and another important effect is spin-Seebeck effect. This was found in Japan in the group of Professor Eiji Saito, and in fact, I was a member in Eiji Saito group, so some years ago, I measured spin-Seebeck effect for various materials. So today, I focus on the Peltier effect, and the Peltier effect is also thermoelectric effect, and it is the inverse effect of Seebeck effect. So this Peltier effect was also studied in spin-caloritronics, and for example, spin-dependent Peltier effect, spin-Peltier effect, and anisotropic magnetic Peltier effect have been studied. But as far as I know, the number of research on spin-related Peltier effect is less than that of Seebeck effects. So maybe this is because Seebeck effect is more easy to measure. But in the application, the Peltier effect is also very important for cooling something. So I believe that the study of new concept of Peltier effect is still important in the spin-caloritronics. So this is my motivation. So today, this is a purpose and outline of my talk. So in the first part, I want to introduce a new material in spin-caloritronics, so chromium-doped manganese antimony. And in the latter part of my talk, using this material, I want to demonstrate a new concept of Peltier effect, so using the first-order magnetic transition of this material. Okay, so the essence is shown in the bottom. So in detail, I will explain later, but the essence is shown here. So, okay, so the junction structures has been discussed in this workshop, but basically the junctions are made of different materials, but our concept is different. So our concept is using different magnetic phases in single material. So we call this magnetic phase junctions. So this is the essence of our concept. Okay, I will explain this later. Okay, so the first is about material. So chromium-doped manganese antimony is, okay, so this is old material. And the end material is manganese antimony. And manganese antimony is a room temperature ferrimagnetic metal. The TC is about 550 K. So the symmetry is centrosymmetric. So in terms of symmetry, this is not interesting. But by doping, the magnetic properties change, dramatically change. So by chromium doping, low temperature antiferromagnetic states appear. And importantly, this transition is first-order transition. Okay, so the situation is very similar to iron rhodium. So this has been studied intensively in spintronics. So this material has first-order ferromagnetic to antiferromagnetic transition. And so, so basically we can expect similar physics to iron rhodium. And the TC of this iron rhodium is about 380 K, so above room temperature. But so chromium-doped manganese antimony, the transition temperature changes from low temperature to high temperature, even above room temperature, by chromium concentration. So about the mechanism of the first order transition, so very famous researcher Charles Kittel wrote one paper about the mechanism, and the title is Model of Exchange Inversion Magnetization. So he proposed that the exchange coupling constant, so-called J, is proportional to lattice constant. So J is proportional to A minus A0. A is a lattice constant, and A0 is some critical value. So by changing chromium concentration or by changing temperature, so lattice constant changes, and when it reaches the critical value, exchange coupling constant, J, shows sign change. So then the ferromagnetic to antiferromagnetic transition occurs. So this is called the exchange inversion mechanism. So similar mechanism was discussed in iron rhodium. And the thermoelectric property was also studied in this material. And this is a report for Seebeck coefficient for polycrystalline samples. So this is the temperature dependence of Seebeck coefficient for x equals 0.05. And in the ferromagnetic phase, the positive Seebeck coefficient is observed, but it suddenly shows negative value in the antiferromagnetic phase. So the Seebeck coefficient shows sign change from positive to negative at magnetic transition. So in this material, so interesting point is in this material, the thermoelectric property is strongly correlated with magnetic states. And the magnitude of the Seebeck coefficient at low temperatures is about 28 microvolt per Kelvin. So this is relatively large compared to typical metals. Okay, so in the physics point of view, so the origin of sign change of Seebeck coefficient and also the origin of the large magnitude of the Seebeck coefficient is important to be studied. Okay, so we prepared single crystals of this material using slow cooling method. So our sample is bulk crystals, and by slow cooling from the above the room the melting temperature, so we prepared single crystals, and the X changes from 0 to 0.1. So we prepared 6 samples, and this is XRD data, and the main phase is manganese antimony phase, as shown by red dots. But unfortunately, so our samples includes impurity phase, mangan antimony 1,1 phase. So this is inevitable in the slow cooling process. According to the literature, this impurity phase is inevitable in the slow cooling process. So, but nevertheless, so our sample is single crystals, so we can cleave easily the sample into AB plane, and the clear Laue patterns were observed for all the samples. Okay, so this is the resistivity data. Okay, so the temperature dependence resistivity for our samples, and X equals 0 shows clear metallic temperature dependence with large RRR. And so for doped samples, you can see clear jump, and it accompanies hysteresis. So this means the first order transition. And the transition temperature increases with increasing chromium concentration. And when we plot the transition temperature in the phase diagram, so our transition temperature is red dot. So the transition temperatures are consistent with all reports. Okay, so then we measure Seebeck coefficient. So this is data for x equals 0.04 and x equals 0. And in the ferromagnetic phase, the Seebeck coefficient is positive, and it shows negative in the antiferromagnetic phase. The temperature dependence is consistent with all the report for polycrystalline samples, but in our single crystals, the transition is more sharp, and the magnitude is also consistent with the literature. Okay, and we also observed the small hysteresis in the temperature dependence of the Seebeck coefficient. Okay, so this is we systematically measured Seebeck coefficient for all the samples from x0 to x equals 0.1. And in the ferromagnetic phase, the Seebeck coefficient positive. And in the spiral phase, it is still positive, but it shows negative in the antiferromagnetic phase. And this negative signal is observed for all antiferromagnetic samples, and the temperature dependence is very similar. The magnitude is also similar for all the samples. To investigate the origin of the sign change, so we performed RPES measurement in collaboration with Professor Ishizaka in University of Tokyo. So this is a band dispersion around gamma point in the ferromagnetic phase and also in the antiferromagnetic phase. Okay, so this is a guide. Okay, so we observed the two bands, alpha band, this is electron band, and the other is a Hall band, beta band. And so the major difference between two phases is the Hall band, beta band, shifts to lower energy in the antiferromagnetic phase. And we observed a small gap between alpha band and beta band. So this is clear if we calculate the integral of the intensity around this region, and we obtain this kind of spectra. And so you can see small dip around here, which corresponds to the gap between alpha band and beta band. And this dip is not observed in the ferromagnetic phase. Okay, so the band dispersion changes at magnetic transition. Okay, so this change in band structure can explain the Seebeck coefficient. So in the ferromagnetic phase, two bands, alpha band and beta band, cross the EF, Fermi level. So in this case, the positive Seebeck coefficient from the Hall band and negative Seebeck coefficient from electron band somewhat cancel following this Seebeck effect for two-carrier case. And but the dominant contribution should be originate from the Hall band, because the Hall band has larger dispersion. Okay, so the larger dispersion leads to the higher mobility. So the larger conductivity leads to the larger dominant contribution of positive Seebeck coefficient in the ferromagnetic phase. But in the antiferromagnetic phase, only the electron band cross the EF. So in this case, the negative Seebeck coefficient is observed. And importantly, this alpha band, the dispersion is very small. So this is like a flat band. So then, according to the Mott relation, in this case, the large magnitude of the Seebeck coefficient is expected. So, okay, so this band structure can explain the large magnitude of Seebeck coefficient in the antiferromagnetic phase, and also the change in the Seebeck coefficient between two phases. Okay, so let's move on to the second part. Okay, so using this material, we demonstrate a Peltier effect. And the Peltier effect is a generation of temperature difference by applying electric current. And to describe this effect, we usually use pi. Pi AB means the Peltier coefficient at AB interface. Okay, so to observe Peltier effects, we need interface. And usually, in Peltier devices, the PN junctions are used. Okay, so the N-type semiconductors and P-type semiconductors and N-type semiconductors. And by applying this electric current to this junction, the heat absorption, the heat release occur at the interfaces. So my concept is this junction structure is replaced by magnetic phase junctions. Okay, so we already know that in the antiferromagnetic phase, the Seebeck coefficient is negative, and in the ferromagnetic phase, the Seebeck coefficient is positive. So if we make this kind of magnetic phase junctions, so we can expect the Peltier effect. So we call this effect single material Peltier effect, and this is the concept of our study. So to make magnetic phase junctions, so this slide shows the procedure. So first, the sample temperature is set at this red star. So the sample temperature is elevated from the low temperature and set at this point. So initially the sample is antiferromagnetic, and by heating of the center part, okay, so I put a small chip heater on the center part, and by applying heater current, so the temperature of the center part increases and reduces to the base temperature. So in this case, the center part becomes ferrimagnetic. Okay, so the center part is ferrimagnetic, and the left and right sides are still antiferromagnetic. Okay, so to these magnetic phase junctions, we apply small electric current to generate Peltier effect, and the resulting temperature difference was measured using thermocouples. And I calculated the Peltier coefficient following this relation. Okay, so this is the main result. The Peltier coefficient as a function of pulsed, the magnitude of heater current. And for small heater current, the Joule heating is not enough to make to reach the transition temperature. And in this case, the sample is still antiferromagnetic. So in this case, the Peltier effect at electrode sample interfaces is only observed. And for strong heater current, the heating is too strong, and the whole region becomes ferrimagnetic. Also, in this case, the Peltier effect at the electrode sample interface is only observed. But in the intermediate heater current region, so we observe peak-like enhancement, and this should be attributed to the Peltier effect due to the magnetic phase junctions. So the magnitude of this effect is about 0.3 millivolt, which is comparable to another spin-related Peltier effect. So this is a base temperature dependence. Okay, so our effect should be observed around this hysteresis temperature. So above hysteresis temperature, the sample is ferrimagnetic and no heater current dependence. And also at low temperatures, the sample is antiferromagnetic and no signal. But in the temperature range around this hysteresis temperature, so we clearly observed the heater current dependence, and this also supports the creation of the magnetic phase junctions. So finally, so I estimate the efficiency of this effect. So the Peltier coefficient can be calculated using the second Thomson relation, the pi equal Seebeck coefficient times temperature. So we already know the Seebeck coefficient. So this is the data. So the change in the Seebeck difference is about 12 microvolt per Kelvin. So using this value, so we can estimate the Peltier coefficient to be 2 millivolt. So this is the ideal value for the perfect magnetic phase junctions. And our experimental value is very small compared to one order smaller than this ideal value. So which means that our magnetic phase junction is not perfect. And so I mean the phase boundary is not smooth, not clear, or antiferromagnetic and ferrimagnetic phases coexist around the interfaces. So if we find a material with larger Seebeck change, and if we make perfect magnetic phase junctions, the Peltier coefficient may become close to the value of bismuth telluride. Okay, so this is the conclusion. So today I focus on very old magnetic material, chromium-doped manganese antimony, and we study this material in terms of spin-caloritronics. And the main finding is we create magnetic phase junctions and successfully observed the Peltier effect based on magnetic phase junctions. So this concept may have some advantage. And one important point is cooling part can be controlled. So because magnetic phase boundary can be controlled easily by heating, by controlling heating, so the cooling part position can be changed. So this cannot be realized in conventional Peltier devices. So this is one merit for our devices. Okay, that's it. Thank you very much for your kind attention.